in the middle of the Jordanian desert, where rainfall averages less than 6 inches per year. The ancient Nabataeans built a thriving city of 30,000 people with running water in every building, public fountains flowing constantly, and enough agricultural surplus to export crops across the Roman Empire. This is Petra, and it shouldn't exist. Cities need water, and there is no water here. Yet the Nabataeans engineered such a sophisticated hydraulic system, capturing flash floods from distant mountains, channeling water through carved rock tunnels, regulating pressure with ceramic pipes, and storing reserves in vast underground cisterns, that they turn a lifeless desert into one of the ancient world's wealthiest cities. And they're not alone. The Romans moved water across hundreds of miles using gravity-fed aqueducts with precision gradients measured in inches per mile. The Minoans had indoor plumbing with flushing toilets in hot and cold running water 3,600 years ago. Ancient civilizations mastered water engineering at levels that most modern cities didn't achieve until the 20th century. This isn't primitive technology. This is hydraulic genius that kept millions alive in places where survival should have been impossible. Water is life. Every civilization in history has risen or fallen based on its ability to secure, manage, and distribute water. Modern cities take this for granted. Turn a tap and clean water flows. Flush a toilet and waste disappears. But these capabilities are recent achievements for most of the world. What's remarkable is that certain ancient civilizations solved these problems thousands of years ago using nothing but observation, mathematics, and brilliant engineering intuition. Let's start with Petra, because it's the most improbable. Walk through the Sick, that narrow mile-long canyon carved through red sandstone that serves as the entrance to Petra, and you're walking alongside an ancient water channel carved into the cliff face. This channel brought water from springs in the mountains miles away, following the natural contours of the landscape with such precision that water flowed by gravity alone. No pumps, no motors, just careful calculation of slope and elevation, ensuring water reached the city. But that's just the beginning. The Nabataeans built a comprehensive water management system that included dams to capture seasonal flash floods, ceramic pipelines to transport and distribute water under controlled pressure, settling tanks to filter sediment, and hundreds of cisterns carved into the living rock to store water during dry periods. These cisterns alone could hold millions of gallons, enough to supply the city for months when no rain fell. The genius is in the details. The Nabataeans understood that water flow could be controlled by pipe diameter and elevation change. They created pressure-reducing basins where rapidly flowing water would slow and settle, preventing pipes from bursting. They used ceramic pipes rather than lead, which the Romans favored, avoiding the health problems associated with lead contamination. The joints between pipe sections were sealed with a hydraulic mortar that hardened underwater, creating watertight connections that survived 2,000 years. The water channels carved into cliff faces demonstrate remarkable surveying capability. To make water flow consistently over miles, you need a continuous downward slope. Too steep and water flows too fast, causing erosion and wasting pressure. Too shallow and water stagnates, allowing sediment to accumulate and block flow. The Nabataeans achieved gradient of about 3 degrees, optimal for sustained flow, maintaining this precise angle over distances of several miles through winding canyons and irregular terrain. They also built channels on both sides of Sick, a redundancy that protected against blockages and provided backup during maintenance. This shows sophisticated systems thinking, not just building infrastructure, but planning for its long-term operation and the inevitable challenges of maintenance in a harsh environment. The result was a desert city with water infrastructure rivaling modern standards. Wealthy homes had running water piped directly into courtyards and private baths. Public fountains called nymphia provided social gathering spaces and demonstrated the city's prosperity. Gardens and agricultural terraces surrounding the city grew crops impossible in a natural desert environment. Petra wasn't just surviving in the desert. It was thriving because the Nabataeans had essentially conquered water. Now shift to the Romans, who took hydraulic engineering to an empire-wide scale. Roman aqueducts are famous, but their sophistication is often underestimated. The city of Rome at its peak was supplied by 11 major aqueducts, bringing over 300 million gallons of water daily from sources up to 57 miles away. This is comparable to water consumption in modern cities of similar size. The most remarkable aspect of Roman aqueducts is their precision. These structures maintain gradients as shallow as 1 in 5,000. That's about 4 inches of drop per mile. Maintaining such precise slopes across valleys, through tunnels, and over bridges requires surveying accuracy that's genuinely impressive even by modern standards. The Romans used instruments like the chorobates, a leveling device using water to establish horizontal reference, and the groma for establishing perpendicular lines. With these simple tools and careful observation, they achieved precision that would shame many modern construction projects. The Pont du Gard in southern France exemplifies Roman engineering mastery. This 3-tiered aqueduct bridge stands 160 feet tall, spans 900 feet across the Gardon River, and was built using fitted stone blocks without mortar. The water channel at the top maintained its precise gradient while spanning this enormous distance, delivering water to the city of Nîmes from a source 30 miles away. The structure has stood for 2,000 years, surviving floods that destroyed modern bridges built alongside it. Roman aqueducts weren't just stone channels. The system included settling tanks where sediment could fall out of suspension, distribution castellum, where water was divided among different parts of the city, fountain providing public access, and sophisticated underground sewers removing wastewater. The Cloaca Maxima, Rome's main sewer, was built in the 6th century BC and is still functioning today. 26 centuries later, the Romans understood water pressure and used it strategically. The inverted siphon was a Roman innovation, allowing aqueducts to cross valleys without building enormous bridges. Water would descend one side of the valley in a sealed lead or ceramic pipe, cross the valley floor under pressure, then rise up the other side to continue flowing. This required careful calculation of pressure forces and pipe strength, and the Romans made it work reliably across their empire. Go further back to the Minoans on Crete around 1600 BCE, and you find even more surprising sophistication. The palace at Knossos had running water, indoor toilets with wooden seats and flushing mechanisms, bathtubs with both hot and cold water supplies, and underground sewage systems removing waste from the building. This is 3,600 years ago, over a millennium before Rome was founded, 2,000 years before most European cities had such amenities. The Minoans built terracotta pipes with tapered joints that fit together, allowing flow in one direction while preventing backflow. They created settling basins and filters to clean water before it entered the palace. They had separate systems for fresh water supply and wastewater removal, understanding that mixing the two caused disease. Archaeological evidence shows they even understood the principle of separating gray water from toilets and black water from sewage, treating each differently. The palace water system included fountains for aesthetic purposes and temperature regulation. In the hot Mediterranean climate, evaporating water cooled surrounding air, an early form of air conditioning. Light wells brought sunlight and air into interior rooms, creating ventilation that helped manage humidity and air quality. The integration of water management with architectural design shows holistic thinking about building as a total environment. The Queen's Megaron at Knossos had a sophisticated bathroom with terracotta tub supplied by pipes, bringing water from roof cisterns heated by the sun. Drainage from the bath went to a separate sewer system with channels designed to maintain flow velocity that prevented sediment buildup. The engineering principles here: slope management, water velocity control, separation of clean and wastewater, are the same principles modern sanitary engineering uses. Ancient hydraulic engineering wasn't limited to Mediterranean civilizations. The Indus Valley civilization around 2500 BC built cities like Mohenjo-Daro with standardized fired brick sewers running beneath every street. Houses had private bathrooms with drainage systems connecting to the municipal sewers. The streets themselves sloped subtly toward drains, channeling rainwater away from buildings. This represents urban planning at a scale and sophistication that wouldn't be seen again for thousands of years. In Sri Lanka, ancient Sinhalese engineers built massive irrigation reservoirs called tanks, some covering thousands of acres and holding billions of gallons. These tanks were connected by canals forming integrated irrigation networks, supplying water to rice paddies across entire regions. The Kalawewa Reservoir, built in the 5th century CE, used a dam over 3 miles long and 40 feet high to create a reservoir that still functions today, 1,500 years later. The Chinese developed extensive canal systems for irrigation, transportation, and water management. The Dujianjian irrigation system, built around 250 BCE, still irrigates over 2 million acres in Sichuan province. The system uses no dams, but instead divides the Min River using carefully shaped levees and channels that automatically regulate water flow, directing more water to irrigation during dry seasons and more to the main river during floods. This self-regulating system has operated for over 2,000 years with minimal maintenance. Qanat systems in ancient Persia represent another hydraulic marvel. These are underground channels, sometimes dozens of miles long, that tap into groundwater in mountain foothills and bring it to surface settlements by gravity flow. The tunnels are hand-dug, often over 100 feet deep, following precise gradients to maintain water flow. Vertical shafts every few dozen meters provide access for construction and maintenance. Some qanats built 2,000 years ago still supply water to modern communities. What all these systems share is an understanding of fundamental hydraulic principles. Gravity provides a motive force for water flow. Maintaining specific gradients ensures efficient flow without erosion. Separating clean water from waste prevents disease. Storing water in reservoirs buffers against seasonal variation. And redundancy and maintenance access are essential for long-term operation. Ancient engineers discovered these principles through observation and experimentation. They couldn't calculate pipe friction losses using Darcy-Weisbach equations or model pressure drops with computational fluid dynamics, but they could observe what worked, refine designs through trial and error, and accumulate knowledge across generations. The result was practical engineering that worked reliably for centuries. The social organization required for these projects was as impressive as the technical achievement. Building aqueducts across tens of miles, carving thousands of meters of tunnel through solid rock, managing coordinated construction across years or decades. These required administrative capabilities, workforce organization, resource management, and long-term planning. Hydraulic infrastructure represented major public investment, and its success depended on maintenance and operation across multiple generations. Modern analysis using technology the ancients never imagined has revealed more about their capabilities. Laser scanning of Roman aqueducts shows consistency in gradient within millimeters over mile-long sections. Ground-penetrating radar reveals sophisticated Roman construction techniques, including concrete vaulting and lead pipe networks still intact underground. Chemical analysis of deposits inside ancient pipes tells us what flowed through them and how water chemistry affected infrastructure longevity. We're also discovering that ancient engineers understood more than we credited them with. The Romans knew adding volcanic ash to concrete made it resistant to water damage, something modern engineers rediscovered only recently. The Minoans understood that U-shaped drain traps prevented sewer gases from entering buildings, a principle reinvented in modern plumbing. Ancient engineers had practical knowledge that worked even if they couldn't explain it in modern scientific terms. There's irony in the fact that many ancient hydraulic systems outlasted their civilizations. Roman aqueducts carried water long after Rome fell. Nabataean cisterns in Petra held water for Byzantine and Islamic occupiers centuries after Nabataeans disappeared. These systems were built to last, often over-engineered for their immediate needs, creating infrastructure that served multiple subsequent civilizations. Modern water infrastructure, by contrast, often has planned obsolescence. Pipes are rated for 50-year lifespans. Treatment plants are designed for current populations without much excess capacity. We build for now, not for millennia. Ancient engineers built for permanence, partly because rebuilding was so difficult and partly because infrastructure was seen as legacy, a gift to future generations. This doesn't mean ancient systems were superior in all ways. Modern water treatment removes pathogens ancient systems couldn't. Our pumps can move water uphill and across obstacles ancient engineers couldn't overcome. We can purify contaminated water sources and desalinate seawater. Our capabilities exceed ancient limits in many dimensions. But in longevity, in elegance of gravity-powered solutions, in integration with natural environment rather than domination of it, ancient hydraulic engineering offers lessons modern infrastructure could benefit from. The Nabataean approach of capturing and storing intermittent water sources is increasingly relevant as climate change makes rainfall less reliable. Roman emphasis on redundancy and maintenance access addresses problems that plague modern infrastructure. Minoan separation of water systems based on quality and use is a principle modern water management is rediscovering. Standing beside a Roman aqueduct or exploring the water channels of Petra, you're encountering engineering that has outlasted empires, survived catastrophes, and continued functioning across 2,000 years. That's not ancient primitive technology. That's sophisticated infrastructure designed with deep understanding of hydraulics, materials, and long-term systems operation. The ancient engineers who built these systems were every bit as intelligent as modern engineers, working with different tools but achieving results that command respect and sometimes envy from their modern counterparts.